Hi guys, my name is Vivek and in this video tutorial we will continue to talk about partitioning in Oracle. Guys, if you have not seen my first video on partitioning, I will highly recommend that you pause this video right now and you go ahead and finish that video. Once you have completed that video, you will be able to appreciate the beauty of this video in a better manner. In that previous videos, I have explained what is partitioning and what are its advantages with the help of real practical examples. Once you have completed that video, you will understand the context of things that are being discussed in this video and you will able to appreciate what are the performance basics in a better manner. Before we understand the performance basics, let's go ahead and understand how Oracle actually stores the data physically on disks. So Oracle uses 3 units for space allocation, and they are blocks, extents and segments, in which block is the most fundamental unit, or we can say at the finest level of granularity, Oracle stores data in data blocks. They are also known as logical blocks, Oracle blocks or pages, and it actually corresponds to a specific number of bytes on a physical database on a disk. Now that number by default these days is 8 KB. Now in a layman terms, what this means? It means every table, index or any object that is being created in Oracle, the most fundamental unit of storage for that is block, or they are constituted by blocks. So every single, like our body is constituted of small cells, the same way every table, object, index, everything is being created from blocks. It's the most fundamental unit of storage. The next level of logical database space is an extent. The next unit is an extent. And what is an extent? An extent is a specific number of contiguous data blocks allocated for storing a specific type of information. Now what does that mean in layman terms? It means certain blocks that are present next to each other, they constitute together and form a block, and they are predefined in number. So here in this figure we have 6 blocks which are next to each other and they form an extent. So it's a higher level of storage unit. So here in the diagram we see 2 different extents that are being formed by contiguous blocks that are together. Now let's understand what is a segment. A segment is a set of extents, each of which has been allocated for a specific data structure and all of which are stored in the same table space. Now what does this mean in the layman terms? It means each table data is being stored in its own data segment. If we have an index, it will have its own data segment. And if we have partitioned the table or an index, they will have their own data segments. Now this concept is actually very critical, and it's, if you have seen my previous video, you would understand what is partition pruning. It's because of this segmentation that we are dividing the different partitions or storing the different partitions or on different segments. That's why we can do our partition pruning. So let's do a quick recap. We have 3 fundamental units of storage: blocks, which is the finest level of granularity. Then we have certain blocks which are stored physically together on the disk, they form an extent. And when we have multiple extents on the same table space that are being used for a particular function, they can be used for a particular table or an index or a particular partition of index or table, we call them as segment. So here in this video, these 2 extents together form a segment. That's the green area. I hope it's clear now what is a block. It's the most fundamental unit. Then we have certain blocks together as an extent, and then we have multiple extents together performing a function known as segments. Guys, I'm repeating this because this is actually very vital, and as we move forward we will mention them again and again. So let's move to our next topic, which is single block IO versus multiple block IO. And in order to understand what is a single block input output or a multiple block IO, let's understand how a B-tree index is stored in blocks. And we will understand that with the help of a transaction demo table, which has 4 columns: transaction ID, transaction type, amount, and transaction date. So in my previous slide, I just mentioned that indexes and tables are stored in blocks. Now we will physically see in SQL Developer that how they are stored in blocks and what is the amount of storage that they consume. So let's quickly switch to our SQL Developer. So I have a transaction demo table here, which has 4 columns. I'm going to create it. The table has been created. I'm going to create a unique index on the transaction ID. So if I don't specify anything, by default a B-tree index is created. I'm going to see if there is any data in my table, which should not be the case, and that's correct. I'm going to insert 1 million rows in my transaction demo table. So the data has been inserted, and as I mentioned that the table data is fundamentally stored on blocks. Let's see how many blocks were created when we created this table. So when I loaded the data in this particular table, it actually consumed 4096 blocks of data, which totally amounts to 32 MB. So that's the number of blocks that were created. So this actually clarifies that yes, the fundamental unit of storage for an Oracle database is a block. Or how you can verify these number of blocks? You can verify that by this table user segments or all segments. It actually specifies the number of blocks that are being used by this particular segment. Now we know that how many blocks are being used by the table. Let's take a step further and see how many blocks are being consumed by our index. So I'm going to analyze my index and validate its structure. Now this particular query will let me know how many blocks have been used by this particular index. So there are 3 key columns that you have to understand at this point of time. The first one is the height of index. So just remember this, the height of index here is 3. Then we have 4 branch blocks and we have 1875 leaf blocks. Now what are branch blocks and what are leaf blocks, we will understand in a moment. But right now let's remember that we have a huge number of leaf blocks. We have a tree of height 3 and the branch blocks are 4. So let's go ahead and see in our presentation how the tree will look like for this particular index. This is how our binary tree will look like. And guys, there is a popular misconception. B-tree in Oracle is not binary tree, it's called balanced tree. And why do we call it that? I will explain that in a moment. But before that, let's just quickly see our tree. So the first block, this particular block, is called the root block. Then we have our middle blocks, and in the last, these blocks are called leaf blocks, and they actually contain the information. This particular transaction ID is stored at this physical location. So they contain a pointer to the physical location of the table where the data is being stored. They contain the row ID. So these blocks in the end, we call them leaf block. So if you remember in our SQL Developer, we saw that we had 4 branch blocks and a number of leaf blocks. Now what exactly are branch blocks? So branch block, it actually doesn't store the physical location where that particular row is being stored in the table. Rather, it has a pointer which actually makes the search more accessible. So it has a pointer to my leaf block. And why do we call it balanced? That's because in order to search any key, it approximately takes the same amount of time. Now, if I have to explain this all in a layman's terms language, let's do that. So if I have a query where I want to retrieve the details from the table where the transaction ID is equals to 1, in that case, it will go ahead the Oracle optimizer will go ahead and use this index. So what will happen? First, it will go to this root block and it will see that, all right, I need to go to the leftmost level or the leftmost level on the next level. So it will go to this particular block, and then again it will be redirected from here to my leaf block, where it actually has the physical location of the row with the transaction ID 1. So once it has the row, it will go to the table and it will fetch the data from that particular block where the row is being stored. Now we call it balanced because we can have any key. Instead of 1, we can have 10,000 and it will follow the same route. First it will go to the root block, where it will identify that it needs to go to the rightmost block on the next level, and there again it will be redirected to the rightmost block of the leaf block, where it will have that particular physical location where the data pertaining to the transaction ID 1 million is being stored. So whether it's 1, 10,000, 1 lakh or 1 million, it's taking us 3 read operations or 3 IO operations to actually reach to the table data. So our blocks which actually have the physical information where the data is being stored on the table, we call them leaf block, and the blocks that are just the pointer to our leaf blocks, we call them branch blocks. So these 4 branch blocks, they don't have the physical location where the data is being stored pertaining to these keys in the table. They only have pointers to our leaf block. We call them branch blocks. And these lowest level of blocks that have actual physical row IDs where the data is being stored in the table, we call them leaf blocks. At this point, let's just quickly recap what we have discussed as of now. So for storage, Oracle has 3 fundamental units: blocks, which is the finest grain, then we have extent, which is formed by contiguous blocks, and then we have segments, which is formed by multiple extents that are in the same table space and which are used for a particular data structure. A table will have its own segment, an index will have its own segment, and if the tables and index are partitions, each partition will have its own segment. Then we discussed about the structure of the B tree index. It's not binary tree, it's balanced tree. And why is that? In order to retrieve the physical location with any index key, it's going to take approximately the same time. That's why we call it balanced. It has 2 types of blocks, the leaf block and the branch block. The branch block does not have any physical information about the actual location of the table or where the data is being stored. It just has the pointers to the leaf block. The leaf block are the lowest level blocks which actually have the physical information pertaining to the data for that particular key. So this is how the data is being stored on blocks for an index. Let's go ahead and see how the data is stored for a table in terms of blocks. We saw that we had 4096 blocks, and this is how they will look like. So we have certain rows that are grouped randomly as a part of different blocks. So this particular is one block. Then we have these 6 blocks, which is actually a subset representation of those 4096 blocks. But this is how the data is being stored. Since the size of the table or the size of the block is 8 KB, it can have more than 1 rows being stored in a block. Just to rephrase this again, since the size of the block is 8 KB, it can have multiple rows in it because the size of the row can be less than 8K. So it can have 2, 3, 4 or as many rows as they can fit in block. The index, they are arranged in a particular manner, but that's not the case with the data on the blocks. They are actually inserted randomly as we receive the data. So if you see, the data is being stored randomly here. We have 12, 54, 78, 93, 784, 509 transaction ID in one block, 110.4 in one block. So while we had sequential data storage in indexing, that's not the case with data storage for a table on blocks, it has random transaction IDs being stored. Now we saw how the data is being stored in index. Now we saw how the data is being stored physically in terms of blocks on the disk. Now let's go ahead and understand our main concept, single block IO versus multiple block IO. So we will understand with the help of an example. So suppose I want to retrieve the details of a transaction with transaction ID 1. So how it will happen? It will happen with the help of the index. So first it will traverse the root block, where it will identify that it needs to go to the leftmost block on the next level, which again only has the pointers, where it will identify that it needs to go to the leaf block on the leftmost level. So now after these three blocks read, we have the data, or we have the physical location where the data is being stored on the disk. But there is a challenge associated with this. As I mentioned that on my index, the data is being stored in a sequential manner in terms of transaction ID. But that's not the case. If we see our transaction table, the data is being stored here randomly in blocks. So we don't have a 1, 2, 3 transaction in a single blocks. If you see here, we have 12, 54, 78 in a single block, 93, 84 and 509 in one block. So this data is not stored sequentially in terms of transaction. So even though I have the exact row ID, I still have to do an operation which is called random IO, which is considered the slowest. So I had to traverse 4 blocks here. The first one is the root block, then the middle block, and then the leaf block. So these 3 blocks which constitute the height of my tree. But apart from that, when I actually went to get the data from my table, then I had to perform a random IO, a sequential IO, which is very costly and is considered the slowest. So in order to retrieve the data a particular row, I had to perform 4 sequential reads, the root block, the next level and the final leaf level, and after that I had to perform a random IO in order to get the data from the block. So when you read less amount of data from a huge table, this is an excellent approach. You only had to traverse 4 blocks. Our table was slightly small, it had only 4000 blocks, but an actually large data warehouse table can have millions of blocks. So in comparison to that, if you are fetching low amount of data, this sounds like a great approach. And there is another misconception, guys, which is very prominent. People think that if your performance is slow, just go ahead and create an index and it will solve that. We will bust that myth in a moment when we understand full table scan or multiple block IO. Now let's assume that right now I only fetched 1 row. Instead, I wanted to fetch 25% of the data. That's a huge amount. So I will have to again and again perform the same operation. Let's try to visualize this. So in the first case, we fetched data for the row first. We accessed a block and now we have that data. We have accessed 3 blocks from our index and 1 random IO, which is considered the slowest on my main table, on my transaction table. Second transaction that I want to extract is for transaction ID 26. So I will go through the same operation. I will go through the root block. I will fetch, I will know that, okay, this belongs on the leftmost data. I will do another random IO and let's see on which block 26 belongs. So the transaction ID 26, it belongs to this block. Remember, we have already read this block when we were trying to traverse for the transaction ID 1. Next, we want to fetch the details of transaction ID 54. so we have to read this block as well. Then I want to read the transaction details for 784, and all these are sequential. When we are accessing using index, we are accessing these sequentially. And remember guys, we are doing a random IO as well, which is the most cost intensive operation. So in order to fetch 25% of the data, I have already accessed 3000 blocks out of 4000 in a sequential manner using random IO, which is considered the most cost intensive operation. And we have not even considered yet this traversal where we are traversing our index blocks. So just to get 25% of the data, if my Oracle optimizer considers the index, it's going to take a lot of time and a lot of IO. So we understood that only if we want to access a minor portion of the data, the index is suitable. But if we want to access a considerable number of data, it's not feasible. So let's see what is the other option that I have. The other option that I have is full table scan, and let's see how it performs. So when we were using the index, we were doing sequential IO, and that too on random blocks. For full table scan, we read multiple blocks at a time, and that too sequentially, which is considered the fastest. So here we read 2 blocks just as reference. Then again in the next IO we read 2 blocks, and then we again read 2 blocks. So in our table you saw that we had 4096 blocks, and in general standard in a single IO full table scan reads 128 blocks. That means in order to read the entire data, it's just going to need less than 40 IO operations. While if we were trying to access the same amount of data using the index, we were almost reading 75% of the blocks, and we had an additional overhead of reading the index as well. So this proves that index is good only when you want to access a very minimal part of the data, which is usually considered 5% to 10% of the data of the table. I mean, right now in this scenario, full table scan looks perfect. If you want to retrieve more than 20% of the data, just go ahead and blindly use full table scan and don't use indexing, and that's what usually optimizer does. But imagine you have a situation where you have a very large database with billions of rows. Even though full table scan is going to be faster if you want to access 20% of the data, still it's going to take huge amount of time, because still you are reading 128 blocks in a single IO, and now you have millions and millions of blocks to be read. So it can take hours just to access the data from that table. Now what's the solution that we have now? The answer is partitioning. So if you are accessing medium level of data, you can use partitioning, and it can actually help you access the data effectively and in a swift manner. And how it will do it? If you remember, I mentioned that different partitions are being stored on different segments. Here comes the concept of partition pruning in picture. As soon as I issue the query, it will know that it only wants to access this particular segment. And once you have minimized the data to be read by 70 or 80%, you only have a portion of the data. You can use multi-block read of full table scan and access the data 70 to 80% faster. Now we know when we want to use or when the Oracle optimizer chooses to use index, when it chooses to use full table scan. When we are actually accessing very less amount of data, it uses index. If you want to access huge amount of data, it uses full table scan. But how do we decide when do we want to partition a table or an index? How do we categorize a table or an index as too big and now is the time to partition it? We are going to learn that now, that when we should partition. So if your table size is bigger than 2 GB, it's a good contender for partition. You should go ahead and think about its partition strategy. Or if you are maintaining rolling data, which means you have historical data, you have data from January, February, March, April, and only the current amount of data is updatable, and all the other months are read only, then you should consider partitioning. And we will understand how range partitioning works and how it will help that in our next tutorial. But this is another scenario when you should consider partitioning. Or when you have a clustered environment with multiple nodes and you want to divide your data across nodes, in that case you can consider hash partitioning. What's that? How do we implement that? All that we will discuss in our next videos. What about index? When should we partition an index? When we want to avoid rebuilding the entire index when the data is removed. So let's say I have a table where I'm maintaining rolling 3 years of data. So as soon as I enter in 2018, the data from 2015 is no more of my use. I'm going to drop that partition. As soon as I drop that partition, if I don't have the partition index, it's going to become unusable. So if I don't want to rebuild the entire index, I can partition it on the same key, which is called local partitioning of index, and we will learn that, but I'm just explaining that if you want to avoid rebuilding the entire index, you can do that. If you want to perform maintenance on part of the data without invalidating the entire index, or if you want to reduce the impact of index queue. So guys, don't worry about it. These things we will understand further in our next tutorial as we move ahead. Let's just quickly recall the advantages one more. So our performance is being improved. We are able to manage, or our DBA is able to manage the objects in a better manner. The availability of the application has improved, and all these advantages can be achieved without changing the application code, or you have minimal changes, because the DML operations, there will be no change in that. They will continue to function in the same manner they were functioning earlier. They will still see it as one object, while behind the scene we are able to improve the performance. At the same time, we are able to manage it in a more effective manner. So these are the advantages that we are getting from partitioning. And guys, there is still a lot more to come. I know that these tutorials have been a slightly lengthy, but I want to make sure that once you invest your 2 hours understanding these video tutorials, you will remember these concepts for your entire life. And don't worry if you have still slight confusion when it comes to indexing or single block read or multi-block read. We are going to repeat this further in our next tutorial with a different example, and hopefully it will be clear then. Guys, it's been a very lengthy tutorial, and let's call it a night. As I have requested you guys before, if you have any questions, please do drop them in the comment section, and please do subscribe to my channel. It actually motivates me to create new contents. Hopefully I'll see you in my next video real soon.